All right, welcome back. So in the last video, we talked about how you can compare the equations for one-dimensional kinematics in translation to the equations for one-dimensional kinematics for rotation. There were a couple of equations that I left off that I'm going to include in this video, and we're also going to talk about translational and rotational kinetic energy. Something that we're going to find in a lot of these videos is that there's going to be very strong parallels between the things that happen when something moves in a linear fashion and when something moves in a rotational fashion. And we're going to see that again here. So to start with, let's consider how we can find what an average velocity is if we know where something starts and where it ends and how long it takes to go between those 2 points. So the equation for that is that so that equation is going to be V average is equal to the change in x divided by the change in time, which is equal to the final position minus the initial position divided by the final time minus the initial time. Okay. We have a similar equation for the average acceleration. So A sub average is going to be equal to the change in velocity divided by the change in time, which is going to be equal to Vf minus Vi divided by Tf minus Ti. So let's draw a picture of what this might look like. So if I have a one-dimensional coordinate axis, so this is just an x direction, and I know that an object is at xi initially, and it has some time ti initially, and it ends at some position xf, and it has a time tf that it takes to get there. What this says is it's going to go from here to here, and I can find what the average velocity is over that traversion by taking the difference in the final position and the initial position, so what I have here, and then dividing by the difference between the final time and the initial time. Okay, so delta, and that's exactly what this equation says, delta x divided by delta t is equal to the average velocity. Likewise, if I know that I have some velocity here, so I'm moving to the right with initial velocity vi, and over here, let's say I have a larger velocity, vf, when I get to this second point, I can find what the average acceleration is by taking the difference between these two. So let's circle this one in red. So this is the difference between Vf and Vi, which is what I have here. Taking that, dividing by the difference in my time, which is what I have here. And I'm running out of colors. So that difference in velocity divided by the difference in time is the average acceleration. Okay. So let's see how this compares to our case for rotation. So if I have an angular velocity, if I want to find an average angular velocity, omega average, this is going to be equal to the change in angle divided by the change in time, which is equal to theta f minus theta I divided by Tf minus Ti. And likewise for our angular acceleration. So alpha average is going to be equal to delta omega divided by delta t. And so this is equal to omega f minus omega I divided by Tf minus Ti. Again, we can draw a picture here to understand what this looks like. So I can draw a circle, and let's say that I have an initial angle of theta is equal to 0, so we'll say that this is theta I. And then I'm going to go to some angle theta f. So my ratio of the difference between theta f and theta I divided by the change in time, so I would also have some times here, so I have a TF and a TI, okay? That ratio is going to give me what the average acceleration, or the average angular velocity is, right? So I have my two times, I take the difference in those, which I have here in this equation here, and then that ratio is what I have expressed here, and that is the average angular velocity. Okay, so we see this parallel between the linear equations and the angular equations again, because in the linear equations I have the ratio of a change in distance divided by a change in time. For the angular velocity, I have a ratio of a change in angle to a change in time. Okay, I won't go through the full argument for the average angular acceleration, but again, you see that it's very similar to the linear acceleration. Okay, so now let's talk about kinetic energy. We have kinetic energy, translational kinetic energy, and rotational kinetic energy. So on the first or the second test, we had our translational kinetic energy that we'll call K sub T is equal to 1/2 mv squared. Now the new equation that we have is going to be for rotational kinetic energy. K sub R is going to be equal to 1/2 I times omega squared. Again, you might get tired of me saying this, but there's a parallel between these two. So with translation, we know that mass tells us how difficult it is to accelerate something. So in this equation for translational kinetic energy, the mass is what tells us how difficult it is to move something. Whereas in the rotational equation, we have this moment of inertia that says how difficult it is to rotate something. We'll talk more about that when we talk about torque. But again, what I'm just really getting at here is to get you to realize that if I look at these two equations, they're very similar. So now what I'd like to do is to continue talking about conservation of energy, both in terms of translation and rotation. So what I have here are two scenarios, one where you have a block on an inclined plane and one where you have a cylinder on an inclined plane. And what we'd like to do is to find what the velocity is at the bottom. Okay, so if this was a question on the last test, what we would have done was we would have started by drawing some energy bar charts. So first let me label, this has a, both of these have some height of h. Let's draw our energy bar charts for the block. So initially at the top, this is going to be some height h above the ground. It's not moving. And so we can say that we have some gravitational potential energy. And at the bottom, it's going to be moving. And so that means we have some kinetic energy at the bottom. Okay? So there's no kinetic energy at the top, and there's no gravitational potential energy at the bottom. Okay? Which means that we can write equations for this to say that the gravitational energy at the top is equal to the kinetic energy at the bottom. Now this kinetic energy is translational kinetic energy, right? The block's not going to rotate. Which says then that mgh, or capital H, is going to be equal to 1/2 mv squared, okay? So if we wanted to, we could take this equation and we could solve for the velocity, okay? Now let's see how this is different for our cylinder on an inclined plane. So for our cylinder on the inclined, okay, so now when we draw our energy bar charts, we're going to have all gravitational potential energy at the top again. And there's going to be no kinetic energy. So K translational and K rotational are both 0. Okay. Now when we get to the bottom, we're going to have 0 gravitational potential energy. So this is 0. And we're going to have some amount of translational kinetic energy and some amount of rotational kinetic energy. Right? So these, they don't necessarily need to be the same height, but as long as they add, the left adds to the right. So now when we want to write this equation, what we're going to say is that UG is going to be equal to KT plus KR. And so what we can say then is MGH is equal to 1/2 MV squared plus 1/2 I omega squared. Okay. Now, when we have a situation like this, when we have something rotating, it's very important that we get our velocity and our angular velocity to talk to each other, right? Because they're going to be related to each other, and we can't leave this equation the way it is because we have two unknowns. We want to get this down to one unknown. So what we can do is we can use one of the equations from the first or the second video that I made, which says that V is equal to R times omega. And so if we want to find what the velocity is, we can replace this angular velocity with omega is equal to V divided by R. And so then the final equation that we end up having is that MGH is equal to 1/2 MV squared plus 1/2 times I times R, sorry, this is going to be V divided by R quantity squared, okay? And this is the final equation that we have. All right, so that's going to be it for this video. In the next video, we'll be discussing torque. All right, thanks.